Welcome to Chapter 3, even though it says Chapter 4, Section 4. This is Chapter 3, Section 4. And in this section, we're going to talk about some application problems that involve systems of equations in two variables. And what I'm going to do in this video is help you get them set up. I've already shown you how to solve systems of equations graphically and using substitution and using the addition or elimination method. So really the only thing that you might struggle with a little bit here is getting the initial system of equations set up. So let's work on making that happen. Here Rachel spent $54 buying 2 bracelets, 3 pairs of earrings. Diane spent $56 on 3 bracelets and 2 pairs of earrings. And we want to find the cost per bracelet and per pair of earrings. So the unknown in this problem is cost per bracelet and pair of earrings. So I'm going to let B equal cost of a bracelet, and I will let capital E equal cost of a pair of earrings. And then Rachel bought 2 bracelets, so the cost of 2 bracelets is 2 times the cost of 1 bracelet. And she also bought 3 pairs of earrings, so we're going to add 3 times the cost of a pair of earrings for a total spent of $54. And then Diane must have been shopping at the same shop because the bracelets and pairs of earrings are going to have the same cost. She bought 3 bracelets and 2 pairs of earrings at a total cost of $56. And if you label this as equation 1 and this as equation 2, you are all set and ready to go. Because none of the terms on the left-hand side of these equations have a coefficient of 1, they all have coefficients of either 2 or 3, I don't think that substitution is going to be your best method here. I would recommend modifying both of these equations so that you have opposite coefficients like we've seen in previous videos. Maybe multiply equation 1 by 3 so that this turns into a 6, and multiply equation 2 by -2 so that this turns into a -6. And then you can add your 2 equations together and eliminate your B term. Solve for E and then substitute back into either one of those equations in order to solve for B. So that technique you can get from watching either of the 2 previous videos. The previous video, 3.3, covered solving systems using elimination or addition, which is the technique I was just describing. In problem number 3, there's something happening here. Outside my door, there's something happening here. Sophie has a bottle cap, and she is... Would you like to bring that in with you? Meow. You want to bring your toy in here? You're making a bunch of racket out here. Hi, come on. Bring your cap in here. Some teachers have children. I have cats. This one's 11 months old and she plays with everything. Anyway, in this problem, this is kind of a mixture problem. So Michelle and Susan use a metal alloy that is 24.6% copper in order to make jewelry. And apparently they have access to some 23% alloy and some 27% alloy, so they need to mix these together in order to form a desired 50 ounces of alloy that's at the 24.6%. So this is a fairly typical style of problem, which is why I wanted to work through this one with you. And the unknown is the number of ounces of the 2 different types of alloy. So let's make a note. We're going to say that X is equal to number of ounces at 23%, and Y will equal the number of ounces at 27%. This is her toy. You believe this? That's all it takes. She's got so many toys. She wants to play with a bottle cap. Okay, so those are our two unknowns. Now what we're going to do is try to create a couple of equations. And the first equation is going to be centered around the amount of actual copper that's in these alloys. So what we want to do is we want to take X ounces at 23% concentration, and we're going to add that amount of copper to the amount of copper that's in the Y ounces at 27% concentration. And what we'll end up with is 50 ounces, I'll put the little OZ on there, at 24.6% concentration. So what we're looking at in this equation is volume and concentration. Plus volume and concentration equals volume and concentration. We're going to turn this into a multiplication problem now, because we want to actually know how much copper is in those X ounces at 23% concentration. Well, that's going to be 0.23 times X ounces. So that's the amount of copper in that alloy. And the amount of copper in this one can be calculated by taking 27% as a decimal and multiplying it by the number of ounces of that alloy that we're working with. And in this equation, on this side of the equation, we've got 50 ounces times the 24.6%, which when we multiply it as a decimal, we end up with 12.3 ounces. Now this is all of pure copper trapped inside of those alloys. So this is going to be one of our equations. That's equation 1. Equation 2 is much more simple. We're using X ounces of one of the alloys plus Y number of ounces of the other alloy, and the result will be 50 ounces of our desired alloy at the 24.6%. That's equation 2. This is the system of equations that you're going to be working with. You could definitely solve this system using substitution. Take equation number 2, make it into an equation that says y equals 50 minus x, and plug it into equation number 1. Or you could take equation number 2 and multiply it by negative 0.23. And that way, you'll be able to add the two equations together and cancel out your x terms. Or you could take equation number 2 and multiply it by negative 0.27 in order to cancel out your y terms when you add those two equations together. So you've got some options, substitution, or either one of the variables could be eliminated. But that's the thought process on getting that one set up. Concentration times volume plus concentration times volume equals concentration times volume. This is a weird little problem. It's almost it's too simplified. It threw me off the first time I looked at it. Here there's an exterminator who's trying to dilute 11 ounces of 60% concentration insecticide by adding pure water. And the question is, how many ounces of water should be added so that the ultimate mixture is at 20% concentration? Well, it's so strange that it throws me every time I read it, because I want to try to set it up like we did the previous problem, but it doesn't get set up that way. Let's see. So we have, let's actually try to use concentration times volume. I've got 11 ounces at 60%, and we're going to add that to how much water? How about W ounces of water, which are at 0% concentration, And the result is going to be the 11 ounces of insecticide plus the W ounces of water, and we want that to be at a concentration of 20%. Should we be trying to create a second equation? I don't think so. Why not? I don't think we need one. How do I know that? Because I've got one equation that only has one variable in it. I'm all set. I don't need a second equation. If I had two variables in this equation, then I would need a second equation with both of those variables in it. But in this case, one equation, one variable. So I'm going to write 11 times 0.6 or 0.60 plus, well, there's no insecticide in here. This is W times 0 equals 11 plus W times 0.2 or 0.20. This is an arithmetic problem. All we have to do is solve for W. This is going to go away because we're multiplying by 0. So I've got 6.6 on the left-hand side. I've got 2.2 plus 0.2 W on the right-hand side, or 0.2 W, by distributing this multiplication in from the right. Subtract 2.2 from both sides and you get 4.4 equals 0.2 W, and then divide both sides by 0.2. If we multiplied both sides by 10, we'd have 44 equals 2W. So divide both sides by 2 and you get 22 equals W. So it looks like we need to add 22 ounces of water. I shouldn't have circled it, I should have put a box around it. That's my final answer. Does that make sense as an answer? Does 22 ounces of water make sense? To me it does, because we started with 11 ounces of insecticide at 60% concentration, and we've tripled the volume without changing the amount of actual insecticide that's dissolved in there. So we've gone from a total of 11 ounces to a total of 33 ounces. So tripling the volume leaves only 1/3 the concentration of insecticide per ounce of water, because we didn't increase the amount of insecticide. So to me, that number is making sense. I like it. I'm sticking to it. An unusual situation where we only had one variable, considering that we're in a section where we're talking about systems of equations in two variables. What's happening here? Oh, I didn't like the language on this one. You could do it, but it's kind of a step up. Let's start with this one instead. Let's actually, maybe we'll finish with this one. So here Miriam received an inheritance of $60,000. She invested part of it at $11,000 and deposited the remainder in a tax-free bond at 12%. And her total annual income from the two investments was $6,900. And we want to know how much was invested at 11%. I'm going to set this up exactly the same way as I did the alloy problem. I'm going to say that she invested X dollars at 11% and Y dollars at 12%. So those are the concentrations. Or sorry, the X and Y represent volume. The 11 and the 12% are the concentrations, so to speak. And now let's talk about how does she actually get the return on her investments. Well, if we take and calculate interest, 0.11 is her interest rate multiplied by the X dollars that she invested at that interest rate. So if 11% of your money turns into interest, the word of translates to multiplication. So 11%, that's the 0.11 of, that's multiplication, X dollars, there's the X. So we've got 0.11X. That's the amount of interest that she earned on that investment, plus 0.12, that's the times Y. That's the amount of interest that she earned on that investment. And if you add those amounts of interest together, you get $6,900. Great, that's one equation. What's the other equation? This is just, this first equation, equation number 1, is just an equation about interest. The second equation is about total money. Total dollar sign. The total amount of money is X number of dollars invested at 11% plus Y dollars invested at 12% equals all of her inheritance. $60,000. Again, this is a pretty easy scenario where you can modify equation 2 and prepare it to substitute into equation 1, or take equation 2 and multiply it by negative 0.11, or take equation 2 and multiply it by negative 0.12 so that you can cancel out your y terms. Just be careful, there's a lot of zeros on the right hand side of that equation. Whatever you multiply by, you have to multiply the entire equation, both the left hand side and the right hand side, so make sure you're distributing your multiplication correctly. Solve for one of your variables, plug that value back into probably equation 2 in order to find your other amount of money that was invested. And then, if you're typing an answer like this into the computer, make sure that you're typing in the correct number. This particular problem is asking us to find the amount of money invested at 11%. I made a note of that right here, that X represents that amount. So if you end up solving for Y first, make sure that you go through that substitution process and end up solving for X, because that's the number that this problem is looking for. I hope that that gives you a good introduction to the process of, not that you haven't worked with word problems before, but translating these word problems into systems of equations is a little bit tricky. And this is a decent sampling of the types of scenarios that you're going to run into, including that one strange scenario where we only had one equation. But build yourself these pairs of equations. Keep in mind that the units, so to speak, should be consistent all the way through an equation. Here, equation 1 was all about interest, left-hand side and right-hand side. Equation number 2 was all about total amount of money. In this alloy problem, equation number 1 was all about pure copper, and equation number 2 was about total alloy. Very similar to interest and total money. Okay. Again, I hope that gives you a good start. And if you're one of my students, work on these problems, practice, show your work, as you saw me do in the previous couple of videos. Show your work so you can bring me some good notes, because if you want me or whoever else is giving you assistance to help you look through and check your work on these problems, it's got to look good. So keep it organized, use a lot of paper, skip lines when appropriate, and I'll see you in the next section. Thanks so much.